Well, thank you very much. You've given me a tall order to live up to myself, apparently. So thank you very much for coming out this evening on a frosty Canadian night, but for a good cause, I'll claim, because there couldn't be anything more interesting, in my view, than this question of origin of life in the universe and how we go from the first stars to ourselves. Okay? This is a question for the ages, and this evening's talk, I hope that I can take you through that and show you, kind of light up some of the highlights in this intellectual voyage that we're going to be doing this evening. And it all keys up on that basic question here. Astrobiology, the field in which we're trying to find life, existence of life in the cosmos beyond the Earth. The driving question is, are we alone? Now that, if you realize it, has guided human thinking from probably since we were hominids. Every culture has had its own answer to this. The great thing about our own culture and why we are privileged is that we can make some progress in this scientifically. It's not just a question that's out there, it's a question we can begin to answer. And I would put the developments that we're doing in 3 scientific revolutions that are going on as I speak, and which you're aware of some of these. One of these is, I'm going to shine a laser here, there it is. So one is in biology itself. If you go back 20 years, biologists did not realize that you could find organisms living, say, 2,800 meters beneath the surface of the Earth here in deep mine shafts, existing in tiny little cracks with a little water and some hydrogen available to energize that life form as we have it here. These kind of bee infernuses shown here. Or in the hot springs in Yellowstone Park, or in the ice in the Canadian Arctic. Organisms have adapted to conditions that are very much like the extreme conditions we're going to find on other planets in our solar system and beyond. So it's not, we already have a partial answer to this. Yes, it is possible to exist in extreme circumstances that we didn't realize that before. The second is, you've all seen, hopefully, Curiosity rover and everything on patrolling the surface of other planets. We've sent satellites now throughout the solar system. We've landed on Mars. On Mars, we've landed on Titan, the moon of Jupiter, Saturn, sorry, and looking for evidence with the rovers for habitability. That's conditions which might have been conducive for life. Was there water there? What state was that water in? Was the planet warm enough? How long was it warm? Etc. Questions of habitability that we're exploring now. And thirdly, a revolution in astronomy. 1995 was the first discovery of a planet around another star. And since then, we have evidence for 1,000 of these, with over 3,000 other candidates available. The data now suggests that there are probably hundreds of billions of planets around other stars in our galaxy alone. So this is a staggering revolution in human understanding, all due because we can build telescopes and machines and develop the technology to answer these questions finally. And that's what's exhilarating here. That's the new step in human evolution. So we can ask ourselves a general question. If we're out to search for life, what should we be looking for? One thing we can do is look for life that's somewhat like our own. Now, maybe that sounds boring and disappointing, but if you're designing billion-dollar missions, you want to be sure to succeed in something that you can understand. We sort of understand a little bit how our biology works, and the question is, would that be universal or not? We simply do not know the answer to that question yet, but begin with what you know and move out from there is the guiding philosophy. So if we do that, and ask how our kind of life works, there's kind of a short list here of things that seem to be necessary for life as we know it. First of all, carbon, the existence of a carbon atom. Okay? Carbon is, as you know, 6 protons, 6 neutrons, and so and a nucleus of 6 electrons whirring around it. So the carbon atom is a unique atom, a unique element, because it is the key element involved in building long-chain molecules. Presumably, life needs to store information, okay? Cells are complicated things. Brains are complicated things. You have to code this in some kind of information storage, and the way our life does it is it codes it in the DNA molecules. Those DNA are innumerable. It's only possible to build those if you've got something like a carbon atom that you can make long chains of and make polymers and other things like this. So carbon seems to be essential. What guarantees you will have carbon in the universe? It's a question we're going to come to. Water. Water appears to be the unique universal solvent in which is necessary for chemistry to occur. And this idea of a habitable planet that we've generated is a key part of the discussion I'm going to have with you tonight. Habitability means having a planet that's warm enough by various means that you have liquid water present on its surface, okay? That's not true and just outside that door right now, but somewhere on this planet it's possible, okay? Bermuda, hopefully. But habitability. If you go out to further in the solar system, we have frozen worlds out there. If you go inside to Mercury and beyond, you've got cauldrons, literally hundreds and hundreds of degrees, not good for life. Energy for life. That doesn't just have to be for the sun. Those bacteria 2,800 meters beneath the ground have found an ideal little niche. They use chemical energy sources. They don't need to drive that with energy from the sun, as we do here on the surface of the planet. So there's a wide variety of energy sources that are available to these extremophiles. Other thing we need are probably rocky planets that are large enough. A rocky planet, we don't know how to make life in the atmosphere of Jupiter. Jupiter's bulk of it is made of gas, same composition as the sun. We don't know how you could put together a biology by things floating around in gas clouds like that. Okay, so this list here, probably we should look for reasons why we have rocky planets and how many of them. Are they habitable? Do they have water on them? Why do they have water on them? Why does carbon appear in the universe? And all of these questions start trickling down to the first stars part of my title, because it's within stars that these basic materials are actually made and injected into the gas of galaxies and is available to form planets and life. So the first part of my story tonight, we're going to be talking about how stars build the materials, include, as an example, carbon. Let's go back to the Earth as it was about 500 million years after it formed. So before this, the Earth might have been hit by many large impacts. The crust could have been molten, the ocean could have formed and evaporated and condensed again. But at about 3 billion years is our first reference point. This seems to be the first possibility that life formed. Our evidence is that it may have appeared that early after the formation of the Earth. So if we look at this planet, then it's dominated by ocean here, you see. Continents weren't up yet. Maybe there were a few volcanic isolated islands, but there were no continents yet at this time. There's gases in the atmosphere, CO2, nitrogen here. We have lightning strikes that are known. There's a lightning strike now. This came out of that cloud. That's associated with volcanic activity. We know that. So this can energize chemistry. This whole setup here, I'm going to come to later in my talk, is a setup that was one of the first experiments done in astrobiology in this 20th century. It was a tremendous driver for thinking about how life may have originated. Setups like this may be very good for generating the molecules that are important for life. So here's our roadmap with that introduction. I'm going to talk about stars, I'm going to talk about the planetary systems that are around them, and then I'm going to talk about the conditions created for first life on these planets, such as our own. And kind of a guiding idea for you is in this very nice slide by David Deamer a few years ago, in which here we've got processes going on in the galaxy. We've got dense clouds of gas over here, out of which stars are forming. We can watch this process. I'm going to take you through a bit of this. Stars form. There's disks of gas that form around the star. At the same time the star is forming, its planetary system is being born. This is occurring at the same time. Okay? The gas is dispelled. The star undergoes its evolution. A star like our sun lasts 10 billion years. And then it reaches an end state here. Massive stars blow up and throw elements that they've been making in their interiors, and I'll talk about that, such as carbon, which is made in the interior of stars, are ejected into the interstellar medium, the gaseous medium, which can be picked up in dust particles. You will be building planets out of this dust and carbon. And the planets will be bombarded here by meteorites and comets. This will bring materials, as I'll show, such as amino acids. Building blocks of protein will be delivered to these watery planets. And down in here, we've got processes by which we've set up what I call a prebiotic state, getting the planet ready to have the formation of life by process we still don't know, but which we're tiptoeing towards, I think. So I'm going to be describing, we'll be up in here forming stars, we'll form planets, we'll look at the delivery of materials like water and biomolecules to planets, and think then, what are those materials like, and how do we get life out of that? First of all, stars. One of the most important things you can ask yourself about a star is, how massive is it? Because if you know that, you will know its fate, essentially. You will know if how long it will live, what kind of elements it can produce, the energy that it puts out to warm planets around it, and a host of other things. So this is, pardon for the graph here, but I'm just plotting in this axis here the mass of stars. So here's one is the mass of our sun. This is 10 times the mass of the sun here. This is 1/10 of the mass of the sun. And this is, I would count up how many stars do I have in each of these mass bins, just count. And I plot up, I get a plot that looks like this. This graph tells you that stars range over at least a factor of 100 in mass. Ours is slightly more massive than the bulk of stars. The typical star in the galaxy is about 1/10 of our mass. Now, that star doesn't get up to very much, as it turns out. Not much energy comes out of it. It doesn't produce many elements, certainly doesn't throw anything back into the interstellar medium. Over here at 10 stars, so stars go up to 100 solar masses actually, and there, those stars actually manufacture things like carbon that is ejected into the interstellar medium, the gaseous medium between stars. It's available to go into things like your bodies, ultimately. Because I should say that every single atom of oxygen and carbon that you have in your body, or anywhere, originated in the heart, was created in the deep burning core of stars, a solar mass and above, and got to us from exploding of stars that are about 10 times and beyond our mass, the solar mass, okay? So we are literally children of the stars, literally. Okay? So energy output, stellar lifetime, production of elements, and this kind of a curve. I don't want to use big words here, I won't tonight, but I will use this word. It's a distribution called log normal, akin to the bell curve, actually, which I think we all kind of have experience of, fortunate or unfortunate. But, we'll go on from there. Now, how does a star control habitability of a planet? The radiation from a star warms a planet. And we're going to ask the question, under what conditions, what positions can we put planets around their stars so that the water on them will be liquid? Remember, it's like a Goldilocks problem. You know, if it's too hot, the water will evaporate off the planet. If it's too cold on the planet, everything freezes. You want to be just right. That's called a habitable zone. So here is an M star. That's 1/10 of a solar mass here. And stars up here are about 10 solar masses, okay? That range I just showed you. So if we're looking down here at the Earth, that's a G star. Here's our solar system. Here is the orbital radius of the different planets. That one means the distance from us to the sun. Jupiter here is at about 5 times our distance. Mercury is about 1/10, a little bit more than 1/10 of the distance. The green shows you what the region is habitable. If you're in here, you're too hot. If you're outside of here, you're so cold that carbon dioxide even freezes out. Now, carbon dioxide is not great for us. It's a greenhouse gas, and we worry about it. But on Mars, you want carbon dioxide because that greenhouse allows the planet to warm up more than the very icy cold conditions it would have otherwise. And if you lose carbon dioxide, you lose that blanket, okay? So this, get control of this. This region out here is uninhabitable, and the green zone. Now, the green zone, you can see as we go to stars from low to high mass, moves outward. The more energy I'm faced with, I have to kind of move back from the campfire, right, further and further away to keep the same temperature. Okay? That's a habitable zone. And the type of star it is determines where that habitable zone will be. And we can ask the question, when we find planets, how many would be in the habitable zone around a star? This is how a star controls the basic conditions for possibility of life on a planet, just by heating it. I'm going to jump a little bit ahead. I'm jumping ahead to planets, but can't resist putting this slide here. So we have been measured, these are about over nearly 1,000 dots here are the measured masses of planets, okay? And what we're doing in this diagram is to plot, one here is the amount of radiation we're getting on our planet that you feel on your skin when you wander out the door there. Well, not today, but you know, on a normal day around. So that is the radiation, we call that flux. That's from the sun, okay? So if we're on a condition, if the condition here were much less flux, then water here, or any other planet, would freeze, right? If we're inwards of this, much more flux, bigger numbers, then we cook. So we know that where the orbits of all of the stars around all of these planets, we know how much flux they're getting onto them. And so we can look here in this bin, right around 1, will be planets whose conditions are like ours, in which they get a flux on them from their stars sufficient to keep water liquid. And here, ladies and gentlemen, so here are the masses of planets. We go from Earth mass up to about 10 Earth masses. So there's a clump here of planets that have been discovered over the last 3 years that should be habitable around other stars, okay? Again, inside too hot, again, yes. So, what about how long does a planet have to be around in order to have life possible on it? That's not a question for us. We know life developed here probably 3.8 billion years after ago, half a billion years after the planet formed. We've got a few billion years. We know this. We know this because from the physics of stars, we can calculate from the mass of the star, we know how long it will be burning its hydrogen through fusion reactions. It converts hydrogen into helium. That burn releases energy. And we know that there's enough fuel in the sun for that to go on for 10 billion years in total. So we've got 5 billion years yet here. That's enough time, apparently, to form complex life. We're here. However, the high mass guys that we've been talking about, those 10 solar mass stars, and those live only a few million years before they lose up their fuel and then undergo a catastrophe like an explosion. So even if you had the ability to build a planet in a few million years, and that's what our calculations say, there would be no possibility for that planet would exist for a long enough time to make anything complex. At least it took a long time on our planet, billions of years, to make multicellular organisms. That's not going to happen. So we see that only around certain stars can you have the possibility of long-lived planets, long enough to have complex life develop. Okay. The high-mass stars have another crucial role. What they do is they make elements like carbon and oxygen. They blow up in their lifetime, and that, as I said several times, puts that into the stellar medium. So this is where the carbon must come that's in our bodies. Okay? So the carbon enters from these high-mass stars, and you could ask a legitimate question. Well, what fluke did those develop? Is there something guarantees the appearance of high-mass stars in our universe? That's why I showed you that distribution. That's that question. Why is it that we do have massive stars? Because if it would be stars just like ourselves, our stars would not be making carbon to throw out into the interstellar medium, so you wouldn't be making planets rich in carbon. Okay? So stars have different roles. Low-mass stars are good abodes for planetary systems, but you build those by the metals, the a metal is anything heavier than helium, by the way, for an astronomer. I keep forgetting myself. So carbon, in my parlance, is a metal. So how do stars form then? I want to take you a little bit into this story. So star formation is a shocking story. Here we're looking at a piece of our galaxy. You know, if you look up the Milky Way, you're seeing the gas of the galaxy edge on, that band across the sky. It's filled with gas. Here's a close-up picture of it done with the Canadian Galactic Plane Survey, a very important way of mapping the gas in our galaxy. You see that it looks pretty disturbed, okay? There's holes in it, there's filaments, there's shock waves running around in this. All of these are created by the explosions of stars, the massive stars that evolve, blow up, and they create shock waves that riddle this gas everywhere. Here we're looking down on the face of a galaxy somewhat like our own. So here are dust lanes, and we're looking down on a spiral galaxy, and those pink dots are regions where there's lots of star formation going. Whole star clusters are appearing. And these too are regions where the gas gets compressed in shocks, okay? Pushed together. The average gas in a galaxy might be just 1 hydrogen atom per centimeter cubed, which is pretty rare. The gas in these clouds might be 100 particles per centimeter cubed, 100 atoms in a cubic centimeter, compared to 10 with many 20 zeros behind it in the sun. So what is the link then between the properties of the gas and the stars that are going to form? So this plot shows you a close-up of one of those clouds that I pointed out in the galaxy. Here, this is a dense cloud that's forming stars. Those circles are very dense regions of gas where stars are forming. And plotted over here is another graph. Here was that distribution of stellar masses that I just showed you a few slides ago. And over here is the mass, you know, we just do the same counting as by how many of these dense regions do we see here plotted as depending on their mass. And you see these two curves look quite similar. In fact, what this tells you is that there are processes going on in this gas that produce this distribution of massive, we call them cores. And if you take a third of the gas that forms in these dense little knots and convert that to a star, you would have an explanation for this distribution of stellar masses. So the processes in the gas that are doing this seem to be responsible for the distribution of stellar masses that we are seeing. This is a great picture. This Herschel Observatory is just shut down, to dismay of many astronomers, because this has been a golden machine working in infrared wavelengths. And it has mapped in detail. Here you can see clouds are these filamentary kind of places. Filaments form when you shock gas, okay? It's a turbulent medium in here. And by turbulence, I mean that thing which makes you feel not very well when you're in a plane ride and the pilot tells you, please buckle up. You're going through turbulence, which is density fluctuations which are rattling your plane around. And the turbulence in these clouds is not only just turbulence we have, but this is turbulence going faster than the speed of sound. So if you were whacked with one of these things, you would really feel it, okay? Fortunately, our atmosphere is not like that, but a plane, that's a supersonic turbulence is, have you ever heard a sonic boom, okay? That's when the jet is going faster than the speed of sound, and it creates a very dense pulse. And you can hear it. That's hit your eardrum, okay? That's what we're talking about here. That's what these filaments are. And in here, you see where the stars are forming. They're restricted to the filaments. And so now we have a picture in which how stars are actually created in dense gas. They're occurring in regions which are highly shocked. They get very dense. And stars in these very dense regions get dense enough that it undergoes gravitational collapse. It's so dense that the pressure in the gas can no longer keep it against its own weight, and it collapses to very high densities. We can study these in computer simulations. So this is a computer simulation done by a group in Britain. These are different times, so you take a ball of gas in your computer, you mess it up with a bunch of turbulence, and over time you see it gets these very highly filamentary things, and A, B, C, D. By here you can see these faint little dots. Those are stars that have formed, just seemingly very much like we're seeing in the observations. Okay, so we can start to mimic this in computers. Don't look at this bottom curve here for a moment. I'm just going to do a little game with you here. We're going to talk about bell curves. Why do we have the distribution of stars that we do? I'm going to tell you now that it has to do with properties of turbulence. Okay? I showed you that stars are always made in turbulent places. How would that determine the distribution of their masses? So let's do a card game. Do a dice game. You take 2 dice, you roll them, and you add the numbers on them. And then you plot, you just make a little graph. How many times did I get a 6 out of that double throw, or a 30 or something? And you do that distribution. This is what the distribution you would get if you did that little dice game of adding the 2 values on your dice. And that distribution is the famous bell curve. It's called a normal distribution. Okay? Do another game. This time, when you throw the dice, you take the 2 numbers and you multiply them. This is the distribution you get now. And this distribution, you see when you multiply things, it's a funny distribution because large numbers are rarer than they are over here. This is the so-called log normal distribution. Okay? It happens when you multiply, a process that's multiplicative, when 2 things multiply one another. And what happens in shock waves? Why does that happen? Because if I have a piece of gas sitting here and it's smacked by a shock wave that runs over it, its density is boosted up by a number. If I hit it with another time, its density is boosted again. It's multiplied by some factor that we can calculate. So because shock waves have this multiplying effect on the density, the distribution of clumps and therefore stars that you get is going to look like the data. So the bottom line here is that this fundamental process we see everywhere in the universe called turbulence is probably what's behind the distribution of stellar masses. Okay? If turbulence is universal in the cosmos, then everywhere you look, you should see, in other galaxies, wherever, you should see that kind of spread of masses going on. So it's related to chaos in a very deep way. Okay? And that's the point I wanted to make. That's the essential point I wanted to drive at here. Let's go on to planets. Not quite at planets yet, but I want to draw attention to geniuses of the 18th century that lit the way, actually, for our modern understanding of how we form stars and planets. German philosopher Immanuel Kant, brilliant French mathematician and physicist Simon Laplace, and the English transplanted German in Britain that developed the world's largest telescope in that century, William Herschel. These 3 figures are the Hubbles of their day. Okay? And what they realized through Hubble's observations of these milky nebulae that you see in the galaxy, fuzzy patches of gas, he thought that stars might be forming out of that. And then Laplace and Kant took the idea, developed the idea that the planets form. Moreover, when this gas collapses, it would form a disk of gas. And out of these disks, you could grow planets. And in fact, 21st century science has confirmed exactly that view in the broad sense of it. That view came possible because of technology developments made by William Herschel. And by the way, the Origins Institute will have a talk in March by Charlie Latta, who's a world expert in observational aspects of star formation, and he will talk about these issues with you in his public lecture coming next month. Here are those very disks. This is a Hubble Space Telescope image. So this is about the size of our solar system, a little bit bigger. We're seeing, there's a bright background here. We're looking to a region where stars are forming. Very high resolution. This is a view with the Hubble Space Telescope. We're seeing light from the bright light from one blocked by something. This is the star in here, and that something is a disk of gas, which we now know to be common around all stars. Go through this phase. So we're bearing down now on the ability with our new generation of telescopes that our Canadian Long Range Plan put us into the world astronomy in this. The ALMA telescope will possibly be able to image the formation of a Jupiter-type planet in such a disk. A key thing about stars, so we can understand now how stars form in some general outline, what types of things they should be doing. I want to emphasize now the important fact of how stars make elements. Now, elements, to build something like a carbon atom, takes this, I'm sorry for this little equation, but I'm just going to explain it to you. You take a helium nucleus, that's helium is 2 protons, 2 neutrons, smash it with another helium nucleus, and you get this guy. That's called beryllium-8. Then you get one more helium to come along and smash with that, and you get carbon. So this is how carbon is made in stars. Our sun will be making carbon one day. Okay? However, while this looks nice on paper, there's another issue in paper that when you try to build beryllium under typical conditions, it just wants to fall apart into 2 heliums again. It does so in a, in a billionth of a second. If you can't get this reaction to go, you can't build carbon in the universe. And therefore, you wouldn't have life. Because we don't know how to make life out of helium. I challenge any biologist to come up with that. That would be quite something. Okay? So, this brilliant person, seen the young man, Fred Hoyle, very well-known cosmologist. Actually, he gave lots of talks on BBC radio about astronomy in the decades ago. Older people may have even heard some of his famous lectures. But he realized that actually it's not so dire. There is, if you work out carefully the strength of nuclear forces and how all of that works in the nucleus, you can find that just lucky enough, the beryllium nucleus lasts a little bit longer than your naive expectation, okay? So he pulled off a mathematical coup d'etat here to demonstrate that. Then experiments showed that he was right. However, if you were to change the strength of the nuclear force that keeps a nucleus together, that keeps, protons bound to one another inside a nucleus, if you change that by a couple of %, you could not produce carbon. That would be impossible. So that looks like pretty fine tuning, doesn't it? Of all the values the strength of the force can have, it's dead on to within 1%. So this has definitely the fact, the laws of physics seem to allow for what we call a bio-friendly universe, i.e. one that can make carbon. Because if you just play randomly with the equations of physics and adjust their force strengths, you have to tune this very, very accurately to find a regime where you can get carbon to form. So what's going on here? Why did this happen? To physics, anything like this smells of fine tuning, and that's a worry. Okay? So you've got at least 2 ways out. One is that somehow this was designed in. There was some mechanism, we don't know what would have fine-tuned parameters to this. There's no physical theory for that yet. The other is, to take a Copernican view, is that maybe we're not the only universe. We're here in this lecture tonight because in our particular universe, the force constants are such that carbon can form and life appeared. But if you just say there could be a random set of universes with different strengths of the different forces, in most of those, you'd never have the chance to build carbon, and hence no life like ours. Okay? This is called a multiverse. And Sir Martin Rees, who is an advisory council of our institute, very famous astrophysicist, has written about this in this book on our cosmic habitat. And Probably, I think we have no evidence, of course, whether we live in a multiverse or not. We wouldn't know how to detect another universe if we stumbled into it. It could be 1 millimeter away if other dimensions were involved, and we'd never know it. Okay? So this is where scientific progress bumps against a problem that at the moment we cannot solve. Supernova explosion, do we actually see this metal? Do we see the carbon getting out into the universe? Well, yes, we do. So one of my favorite pictures taken with an 8-meter telescope, here's a spiral galaxy. A supernova explosion went off here. When it does, a supernova can be as bright as the entire galaxy for a week. So you can really pick these out of an image. Here's a blow up, and then you can analyze the kind of stuff that this is associated, the gas associated with this ejecta from the supernova. And you can measure here that they're 1/10 of the mass of the sun of metals. Elements like carbon, oxygen, et cetera, have been blown up and into the interstellar medium, right here. Okay? So there are the metals. There's carbon coming into the gas of the galaxy from an exploding massive star. So we have direct evidence for that part of the story. I promised you we'd go back to first stars, just very briefly. We now know from cosmology that our universe, that should be 8 there, 13.8 billion years. But here we are at this, and we look back in time. If we look back in time, you'll see galaxies like ours, but if you go back far enough, galaxies get smaller, they get patchier because they haven't evolved very much yet. Go way back to this time, about 400,000 years after the Big Bang, is the place where the first star in the galaxy is formed. And the machine that we're about to launch in 2018, the JWST, James Webb Space Telescope, will be tasked with trying to get as far back to find some evidence for these first stars. Okay? And here is a computer simulation how the first star may have formed 400 million years after the Big Bang. So these are pictures here of kind of a filamentary gas setup. Gas is falling into what we call a dark matter halo. Most galaxies are dominated by unseen dark matter. Here we have gas falling into that with time, and we're zooming in on different scales. This is the scale of distance of a few 100,000 times the size of our planetary system here. Here's a larger scale, 6 parsecs, et cetera. But we zoom in and we see process very akin to what we're observing that I just showed you. We see some evidence of a single star undergoing a collapse to a very dense region. So these first stars are forming in gas that's only made of helium and hydrogen and nothing else. Collapsing and forming the very first time that light can shine out in the cosmos. Let's go to planets. There are 1,000 planets known, and this plot here kind of shows you where they are. Where are they with respect to their stars? And what is their mass? So here is the mass of Jupiter, this line across here. 1 is 1 Earth mass, okay? These are the orbital radii of these, what orbit. 1 means the Earth-like orbit. And what you can see is for many of these systems, you have Jupiters, mass of Jupiter here, in orbit where the Earth is, for God's sake. Here you can see things almost the mass of Jupiter. These green guys here, they're orbiting inside the orbit of Mercury. These planetary systems are nothing like ours. It's starting to look as if we're the weirdos. The solar system. Okay? This is the architect. I'm not going to go through this slide. I want to tell you a little bit. How many of you may have been at the Origins talk we had? We had a person from the Kepler Observatory. So this is an observatory space telescope. And what it does is it just looks at, to find other planets. One good way of doing it is just stare at another star. Okay? If there's planets in orbit around a star, here's the lit up disk of the star. Say a Mercury comes by like this, and as it transits in front of the face of the planet here, it's blocking some of the light from my hand. And you can measure that little dip in the total light that you're getting from a star. Okay? And if it occurs regularly, if you're in orbit, you watch it for a few orbits and see that it regularly goes down and comes up, you can actually measure the size of that planet, and you can start determining something about its orbits, etc. So it's using this machine that we're able to find, having stared at about 150,000 stars and just staring at it and watching how the light rises and falls in these. We've identified a whole host of planets. So here, those 12 planets I showed you in the beginning slide of the habitable ones, these are artists' impression of them. Here is the Earth to give you a scale, and these are our best shot at other habitable worlds now. They're larger typically than the Earth. These are called super-Earths, several times its size and mass. The color is shade that the artist is given here is indicative of the light from its host star. So a lot of these things are the reddish because they're around low mass, cool stars that are more red light than yellow. Here's one of the examples. And Kepler 22b here is shown for its star and its orbital radius. The green is the habitable zone around its star. And you see it's just inside, it's a little bit hot probably as a planet. Maybe it's a little bit like Venus, but it's just probably marginally habitable here. Okay? Again, the green is it's the set of radii for which water should be liquid. And for comparison, here's our own solar system. Okay? Another interesting thing about planets is remember, how do you make rocky worlds? Rocky worlds you have to have what's called metal, like carbon, oxygen, silicon, iron. Things like this is how you build planets. And what we can do, we can measure how much of these elements are associated with the planetary system by looking at the light from their stars. And their stars contain a record of the gas out of which the planetary system is formed. So we just look at the light from a star and we can ask the question of what metals do we see in that spectrum of that. And here's a really interesting plot. So one here indicates the same metallicity, as we call it, as our sun. If we go this way, we're a tenth of the metallicity of the sun, and this way is more metal-rich. Plotted up here is the percent of stars that have planets around them, massive planets, like Jupiter's. And what you see is that you run out of planets when you become if you become much poorer gas, much rich in metals, you lose the possibility to make big planets. Now, this tells you something really else interesting about the origin of life in the universe, as is captured here. Because now you can ask a galactic scale question. You can say, let me look around in the galaxy. Stars are blowing up everywhere, putting rocky materials like silicon, oxygen, carbon, and other things into the gaseous medium as a function of time. So time goes this way. Here's 13 billion years ago. And here's the orbital radius of a star. And you can ask the question, where in the galaxy and when do we have gas that's enriched enough that we could start forming planets? That's what's called the galactic habitable zone. And that is the green area in this plot. So here, the first green you see occurring about 8 billion years ago. Okay? And that occurs, our orbital radius is about here. So 8 billion years at about our position in the galaxy was the first time our galaxy could have formed planets. And then, hence we're in time, we enrich gas that's to larger galactic radii and to smaller ones, but this tells you that if our planetary system formed 4.5 billion years ago, the first one could have formed 8 billion years ago. So again, we're kind of typical. In the life of a galaxy, we're not the first planet that appeared, but we're just kind of average. How do you make a planet? Well, you have to take little dust grains shown down here. That's a micrometer. Here's a millimeter scale. There's a meter, so that's a boulder. A kilometer, part of the city of Hamilton. 1,000 kilometers, we know where that is. And you just take little dust grains in these disks. They collide with one another. They build. And over about 100,000 years, you can start building objects that are the size of planetesimals, shown over here. Planetesimals then start colliding with one another to build bigger things called planets. Now I want to tell you the water story. Where did the planets get their water from? Well, let's line up. I'll just tell you the fact that you have to have these 1,000 kilometer, 100 kilometer sized bodies collide with one another, and that's how you accumulate the mass to build a planet. Okay? So here what we're going to do is we're going to add one more thing to this picture. If we're inside twice the distance, about the orbit of Mars, and inside that orbit, the gas out of which our planet formed was too hot to have ice form. And if water can't condense into ice, it can't get trapped by the planet. So if the Earth was formed right here where we are, our Earth would have been completely dry. There would be no water on it, because water could not have condensed on a planet at our orbit. It's just too hot here. However, if you go beyond the orbit of Mars, so any bodies out there are cool enough that ice could have condensed and they'd be watery, okay? So that's this, the blue dots. So here we line up a bunch of planetesimals. There's water-carrying ones, there are dry ones. We put a Jupiter here. This is distance in orbit, 1, 2, 3, 4, 5 times the Earth's orbital radius, sitting here. The gravitational pulls and tugs of that massive planet perturb the orbits of these guys. The amount of perturbation is measured up here, a bit complicated, but E measures how eccentric, how elliptical orbit that is. Okay? The Jupiter gives little kicks to these orbits. When you give a kick to a circular orbit, it wants to go in orbit like an ellipse, like a comet orbit, if you know what a comet orbit is like. That means that these things can collide with one another. And so what this computer simulation shows is over 1 million years, 10, 30 million years, 200 million years, over that process, the size of the dots indicates how big a planet that you're making. The color indicates how much water it has. If it's blue, there's a lot. Red, there's nothing. Over time, more and more collisions build up larger and larger bodies, clearing this out. You see that by the end, we're left with 5 terrestrial planets, rocky planets, and the color code for how much water they contain. If you look at this little bar graph down here, this tells you how many Earth oceans of water do you have for these planets. So how many times did you get 1 to 10 Earth oceans worth? That's here. That's about, here's a number, it's about 15%. Okay? So you see that most of the time, planets get up to 100 Earth oceans worth of water. 100. Now, there would be no possibility of having continents appear above 100 Earth oceans of water. These would be water worlds. We don't know if you can have life form on a water world. There's lots of water, maybe too much of it. Okay? But the question is there water around for forming planets? The answer is absolutely yes. Water is actually abundant. And there's a few cases where you have more than 300 Earth oceans worth of water. And here there are a few that are very dry planets. Our own planet probably has 5 or 6 Earth oceans worth down way below the crust in that molten stuff that's making the lava and making planet plates float tectonic motions across, making continental drift possible. So the computer calculations tell us pretty accurately that probably we have about 8 Earth oceans worth of water in our planet. So we get water. This is how we get rocky worlds. I've told you how we get carbon. What about life? I hope I have 10. I know I'm going a little bit over, but if I would have 10 minutes yet. So let me tell you this story. We now need to equip this planet with things that are building blocks of life itself. And what are those building blocks? For us, they're complicated molecules. As an amino acid. Amino acids, if you take proteins apart in our bodies, you come to a set of about 20 amino acids that have been built by life, that are used by life to build all the proteins in your body. Now, these two gentlemen in the early 20th century made a remarkable claim. Before the 20th century, the idea that life could occur just anywhere at any time was a common idea. It was called spontaneous generation. And it was Louis Pasteur, the person who gave us the pasteurization process. He was the chemist that showed that life didn't occur spontaneously, like in dirty rags that you left in the corner, or, et cetera, the claims that had been made. Okay? He proved that the common idea that life occurs at any time, anywhere, in dirty rags or what have you, was not true. And that experimental insight of Louis Pasteur was taken by these two gentlemen. Oxford, clearly, early 20th century, just look at his dress, and a Soviet physicist, Oparin over here, wrote a remarkable book on the origin of life. And to them, life formed only once, probably close to the time when the planet itself formed. It formed in some kind of a hot primordial soup, and that in order to understand how this origin occurred, if you had sufficient knowledge of physics and chemistry, plus some idea of Darwinian evolution, that there's a self-selective process that culls out things that are better able to survive in some environment. These three things together would give you appearance of life. If we took a timeline of life on our own planet, this is kind of one of the best available compilations here, this storyline here. I've taken you through this part, formation of planets, through the galaxy even, and to this point where we have, at 4 billion years ago, a planet that's ocean has settled down, that's ready. From this side, the biologists told us from evidence from microfossils, et cetera, that the best evidence we have is that there's some evidence that life may have started 3.8 billion years ago. And in here is the grand mystery. No one knows how it started. Okay? So this is what we're trying to understand. We have to have some basic building blocks, we think, to building life, and these are the molecules, the more complex molecules, amino acids, things that you make your pieces of the DNA, etc. Where do we get these biomolecules? How do they come about? Well, interestingly, one way to get them is just from meteorites that are crashing into the Earth. Go out now and pick up some species of meteorite. Here, the Murchison meteorite that fell in Australia. It's got about 70 of these amino acids in it. These meteorites are actually chips off of these 100-kilometer bodies that we've been talking about that build the planets. And it turns out that if you look at the structure of these, this is the temperature structure of such a planetesimal. It can, in the first million years, it's actually still warm. The decay of elements in it, like uranium or radioactive species, keep this ice ball warm enough to actually have chemistry. It's about 100 degrees in these things, and conditions that you can make molecules. This is a compilation here of certain kind of meteorites called carbonaceous chondrites. These are carbon-containing meteorites that fall to Earth. And these are the list of 20 amino acids used by life. And we record here in this compilation for different types of meteorite classes. It's obviously a sweet spot in here, but the relative abundances of these amino acids. Glycine is the simplest and the most common. This is ordered, so this is the most complicated chemical structure. This is the simplest in these graphs. See, the simplest chemical amino acid is the most common in all of these different types of meteorite. We've seen amino acids in comet tails. Comet streaks by. Send the spacecraft there, flying through the tail of the comet, collect the dust grains that are behind, bring it back to Earth. That experiment was done about half a decade ago. Collect the samples, and in a 3-year piece of work to demonstrate this, it was found that glycine was discovered in this. Okay. So conditions in icy grains in space that are activated by a little light falling on it can activate the chemistry here and produce. This is a structure of an amino acid. It's a little bit late, I won't take you through that, but an amino acid's got certain chemical groups. There's the carbon atoms. An amino is nitrogen and hydrogen, and the acid is this little group here. And you can have a wide variety of aminos by what you attach at this position of the carbon, for those of you that know a little chemistry. You can also build these, and I mentioned in the beginning of my talk, there was a famous experiment that took the conditions of an early Earth that I showed you in my opening slide, or set of slides, and put them into a chemical laboratory setup shown here. This is Stanley Miller in 1953, most important experiment in astrobiology, which demonstrates that if you've got water vapor here bubbling up, there's a warm ocean here, water vapor, here's a cloud where you've got a chamber here with gases thought to be part of the early Earth, some hydrogen, ammonia, and other type of gases in this reaction vessel, strike lightning through it and collect down here in this cool flask. What you get out of this, you will find amino acids. It takes a day or two. You can do this in a laboratory experiment pretty easily. This seems to be Oparin and Haldane's idea. The laws of physics and chemistry are creating, out of fairly natural conditions you expect on an early planet, biomolecules. If you didn't get them this way, you could get them from meteorites that are falling onto your planet. And another way you can get it is by here, looking at the bottom of an ocean. This is a photograph of the bottom of the ocean at a trench where there's lava coming out, middle of the Atlantic Ocean, called a hydrothermal vent. And here there's a possibility for having chemistry here. This is a place like bacteria love to gather around here. They feed on the hydrogen sulfide. It's a nice source of chemical energy for their kind of metabolism down in here. High temperatures, but here again might be a place that's a good place for life. Don't look at that equation over there, that chemical equation. Let me just tell you. The simplest way you can get glycine is very easy. You take a few noxious substances. You take formaldehyde, and in water, you mix it with hydrogen cyanide and ammonia, warm gently, and you get glycine, the simplest amino acid. All of these gases are common in those disks of gas I was telling you about. We've detected all of these components in the gas around young stars. So these kind of processes probably what created, we're showing the amino acids in meteorites. This is work that calculations we've been doing, taking that synthesis path and comparing to the data for a variety of meteorites. The green is the theory, the red is the observations. We're on a track to understanding that composition. What about the first cells? We think that life needs a bag. You need to isolate a bit of chemistry here, control it in some sort of a bag, a cell, to have reactions to go. And the way you can do that is take that bit of that Murchison meteorite, grind it up, and suspend in water. It has fatty molecules in it. And those fatty molecules spontaneously organize themselves into these kind of layers, which are like the walls of membranes. There's even experiments on, I don't have time to go into this. And let me close with the following thought. What is the step to the genetic code here? We're making our genetic code works by, there's 20 amino acids and DNA, and these work together to make proteins and replicate the information through the DNA and to propagate this information to future generations. It's a protein DNA code, very sophisticated. We have no idea how this arrived in. Fact is, it does exist. We're very primitive ideas of how it could have come into being. But This plot here is, I wanted to draw your attention to one final thought. How can we precondition the formation of such a code? If you're going to build proteins, you're a DNA molecule, let's say. You're looking around for amino acids that you can build into a protein. Presumably, the most common amino acid is the one that you're going to start incorporating into your code. Those 20 I've talked about turn out to be among the most common amino acids. This plot that we did a few years ago, Paul Higgs and myself, shows that the relative amount of those amino acids compared to glycine here depends on how much energy you took to make that molecule. The more energy you need to make it, the rarer it is. That's what that line shows you. So the genetic code is this table. What the genetic code is, it's that you've got amino acids over here, and you have to take an amino acid and guided by the DNA through RNA, but you have to build this amino acid, code for it, so you can slide it into the relative position in building your protein, okay? So the code takes, there's 3 bases in DNA. I'm relying on hopefully some knowledge of DNA that you may have. You've got 4 bases in DNA. And if I take combinations of 3 letters, U, C, A, and G, those are the 4 bases. If I take 3 of them, that codes for a codon, it's called. And the genetic code is this 64-element table that I'm showing you here, which links codons with the amino acid that they code for, that they line up with. You can see glycine here. Right over here, there are 4 different combinations of these 3 letters that code for glycine, and so on. So, the frequency of amino acids we're having is dictated by thermodynamics, just how much energy it takes to meet them. This is universal. The early code probably used a smaller repertoire of amino acids, probably just 10 that are easily found in meteorites, etc. The other 10 life probably makes and builds itself. So the early genetic code probably made advantage of these basic building blocks, chose the 10 most common ones, and started to build a code that was somewhat functional. It used the lowest cost amino acids. We know that you can build functional proteins out of a simpler set of amino acids. As time went on, as you start to get the first genetic code, then you can start picking and choosing more amino acids to make the code more specific, not just to grab something, but to design a careful protein tool to build something with. So our best thoughts so far are that the genetic code started in this kind of a soft way using these basic materials and then refined itself quickly, so that by 3.5 billion years ago, it's probably arrived in the form that we now have it. It didn't change since then. That's where Darwinian evolution comes in. Very effective in choosing out the most suitable combinations. The ones that make the chemistry work faster will be the ones that go forward. Okay. So I'm way over time here, for which I apologize, but let me just summarize. I've tried to show you that a universality. The processes by which you build stars should occur everywhere in the galaxy. We have information and data for that. That planet formation and star formation, they're hand in glove. They're different aspects of the same kind of process. Stars themselves and their properties originate some very deep idea of chaos, turbulence in particular. I've showed you that it's very natural to form elements like in what stars, which are the important stars for forming the elements that are important for life. This is also pretty universal. Tried to argue with you that the evidence, the calculations show that the amino acids that are used by our code, there's thermodynamic reasons for it. The simplest amino acids are the most common because you need less energy to make them. It's that simple. All of this comes down to this question. All these processes I showed you are everywhere. We have now hundreds of billions of planets that are suggested by our data. Carbon should be everywhere, etc. do these universal principles mean that we are not alone? I come back to my original question. Are we alone or not? I've tried to show you that conditions for creating life are everywhere, and there's energetic reasons for expecting these things. We can't really answer this yet. There's a sophisticated mathematical analysis that if you have only one of something, us, then the probability, it could be that we truly are the only planet with life on it. That's possible in the cosmos. However, if you turn that to 2 instances of life, if we find more life on just one more place aside from the Earth, then your probability swings wildly. And it starts becoming, the probability suggests that it could become common, or at least not terribly rare. That's why it's important to find that next planet that has life, because that will change our complete concept of whether it's possible or not, even in spite of all these universality arguments I've given you. We've got more machines coming along to do the work, so I think we just live in a very privileged time and to answer these questions. Thanks very much.